In just one night, a 10-story building rose in the middle of a Chinese city, a speed dozens, even hundreds of times faster than how high-rise buildings are typically constructed in the United States. What truly stunned the construction world wasn't what happened on site, but what had already taken place long before the cranes arrived. Massive concrete components, each weighing tens of tons, were manufactured inside factories with tolerances of just a few millimeters. They were then transported directly to the construction site and lifted into place like giant building blocks. No prolonged concrete mixing, no waiting for curing, no cumulative errors from floor to floor. When construction becomes a process of lifting and assembling, the way humans build high-rise structures begins to fundamentally change. So how effective is this approach really? Let's find out on Mandarin Tech. Under the pressure of rapidly growing urban populations, construction is no longer just about housing. It has become a matter of survival for healthcare infrastructure. The COVID-19 pandemic in 2019 exposed just how fragile that system really was. As infection numbers grew exponentially, many countries saw their hospitals overwhelmed, beds running out, and time becoming the scarcest resource of all. According to estimates from the World Health Organization, the pandemic claimed roughly 15 million lives worldwide, leaving behind a level of fear and uncertainty rarely seen in modern history. At the epicenter of the outbreak in Wuhan, China chose an unprecedented approach. On an empty site, Huoshenshan Hospital, a two-story facility with more than 1,000 beds, was constructed and put into operation in just around 10 days, at an estimated cost of 60 to 70 million US dollars. Shortly after, Leishanshan Hospital followed, adding another 1,600 beds in less than 2 weeks. Each patient room was designed for isolation and came pre-integrated with electrical systems, oxygen supply, and medical waste treatment from the very start of assembly. As the construction industry is forced to deliver higher speed, greater precision, and repeatability on an industrial scale, precast concrete twin walls have emerged as an inevitable solution of the modern era. Inside the factory, the production process begins with details that may seem simple at first. Steel pallets are thoroughly cleaned, checked for flatness, and coated with release oil to create a precise casting surface for each wall panel. Magnetic formwork is then positioned according to the exact panel layout, defining wall edges, window and door openings, and surface penetrations, ensuring that no concrete leaks during casting. Once the formwork is secured, spacers for the concrete cover are placed before the reinforcement is installed. Steel reinforcement is cut, bent, and positioned directly on the pallet with accurate spacing and correct elevation. This reinforcement system forms the structural skeleton of the first concrete layer. C40 grade concrete is then evenly distributed by machine and compacted using computer-controlled vibration tables to eliminate air voids and achieve a high-quality surface finish. The pallet carrying the first concrete layer is transferred to a heated curing chamber for approximately 12 to 24 hours, allowing the concrete to reach its initial strength. In the next stage, lattice girders are installed to connect the two concrete layers, while spacing elements maintain the exact wall thickness. The second concrete layer is cast in the same manner as the first. While the concrete is still fresh, the first layer is lifted, rotated, and precisely placed onto the second layer, forming a complete twin wall unit. The finished element then undergoes further curing until it reaches its final strength, ready to leave the factory and move on to on-site installation. But for those prefabricated buildings to stand firm, the massive loads above must be transferred safely and reliably into the ground below. Steel molds ranging from 12 to 24 meters in length are first prepared, thoroughly cleaned, checked for straightness, and coated with release oil to form each pile with high precision. Inside the molds, main reinforcing bars and stirrups are cut, bent, and assembled into load-bearing steel cages made from high-strength steel, capable of carrying enormous compressive forces deep underground. Once the reinforcement cage is secured in position with spacers, high-grade concrete, typically between C40 and C60, is poured continuously along the length of the mold. Vibration systems operate simultaneously to eliminate air voids and ensure dense, uniform concrete that transfers loads evenly along the pile shaft. For pre-stressed piles, steel tendons are tensioned in advance according to design specifications, usually to about 70–75% of their design strength, allowing the pile to better resist both compression and bending during driving or pressing. The finished elements are then transferred to steam curing chambers at temperatures of approximately 60–80 degrees for 8 to 12 hours. When the molds are opened, piles measuring tens of meters in length emerge with sharp, clean surfaces and a flawless finish. From the foundation components prefabricated in the factory, the construction site moves into the phase where the foundation is formed under real geological conditions. At drilled pier or wet shaft locations, a telescoping drill shaft is lowered into the ground, typically with diameters ranging from 600 to 200 millimeters, using hardened cutting teeth to penetrate weak soil layers. At the same time, a stabilizing slurry, made from water, polymers, or bentonite, is continuously pumped into the shaft to support the sidewalls and prevent collapse as depth increases. Excavated soil and excess slurry are removed back to the surface, allowing the shaft to maintain its design shape and dimensions throughout drilling. Once the required depth is reached, the reinforced steel cage is lowered into the shaft and aligned precisely with the center line and embedment depth. Concrete is then pumped from the bottom of the shaft using a tremie pipe, gradually displacing the slurry and forming a dense, solid pier. At the completed pile heads, starter reinforcement is installed to prepare for connection to the foundation structure above. Precast concrete foundation beams, typically 6 to 12 meters long and weighing tens of tons, are lifted into position by crane, placed directly onto the pile heads and fixed using grout or concrete infill. The entire process is continuously monitored using laser positioning and elevation control equipment, ensuring the foundation system forms a continuous load-bearing frame ready to receive the loads from the superstructure above. Once the foundation system has been completed and reached its required design strength, the construction site moves into the assembly phase of the building's superstructure using precast concrete elements, where speed and precision become critical. Precast double-wall panels are first delivered from the factory in a carefully planned installation sequence. Each panel typically measures 3 to 6 meters in height, is 20 to 30 centimeters thick, and weighs between 5 and more than 20 tons. Tower cranes or crawler cranes lift each panel into position, while installation crews align center lines and elevations using laser systems, keeping tolerances within just a few millimeters. Once the wall panels are set, starter reinforcement projecting from the foundation is connected to the reinforcement within the panels. The joints are then filled with non-shrink grout or high-strength concrete, forming rigid connections that transfer loads directly into the foundation system. Next, precast or filigree floor slabs are installed. These slabs typically measure 2 to 3 meters in width and up to 8 to 10 meters in length. They are placed directly onto the load-bearing walls and secured using connecting reinforcement. A thin concrete topping layer, usually 50 to 70 millimeters thick, is poured over the slabs to tie the individual elements together into a single continuous floor plate. This assembly process is repeated floor by floor, allowing the structure to rise vertically at a steady pace, often requiring only a few days per floor, rather than weeks with conventional construction methods. The blending process begins as each homogenized raw material is pulled into the automated dosing system, where belt scales continuously measure and adjust the proportions according to the plant's design formula. Once the mix meets the required ratios, it is sent directly to the grinding unit, the most energy-intensive stage of the entire line, and the step that ultimately determines the quality of the raw meal before it enters the preheater tower. Depending on the plant's technology, the material is fed into either a vertical roller mill or a multi-compartment ball mill, massive machines capable of continuous operation and handling anywhere from 100 to 500 tons per hour. Inside the grinding chamber, the intense compressive forces and friction from the rollers or steel balls break the material down to particles smaller than 90 microns, producing raw meal with a high level of uniformity. Some older production lines still use the wet grinding method, adding water to create a slurry. This approach makes chemical control easier, but consumes significantly more energy, so it is gradually being phased out in favor of more efficient dry grinding systems. Throughout the entire process, all operating parameters, including feed ratios, grinding speed, fineness, and gas temperature, are monitored in real time by the SCADA system to ensure the raw meal remains stable and consistent before moving on to the next stage. Heat from the hot gas flow spreads through the preheater tower, but the raw material must follow its own path before entering the harshest stage, the rotary kiln. From the top of the tower, the limestone clay mix drops through tall cyclone chambers, spiraling with the rising hot air. Each cyclone works like a natural heater, raising the temperature of every particle to around 850 degrees C within seconds. In the calciner, the heart of the tower, carbonates break down almost completely, turning the raw meal into minerals ready for high-temperature reactions. This multi-stage structure operates like a vertical river of material, weaving through steel chambers and absorbing energy from the burners below. Coal was once the main fuel, but to cut costs and emissions, many modern plants now add alternative fuels. The deep rumble of the rotary kiln mixes with the glow of the red-hot flame, creating a steady industrial rhythm. Inside the long steel tube, raw meal from the preheater drops in and slowly slides along the refractory lining, turning with the slight tilt of the kiln. As it moves into the hottest zone, each grain of limestone and clay is exposed to more than 1,180 degrees, where their original structure begins to break down and reorganize into new minerals. At this temperature, CaCO3 rapidly decomposes, releasing CO2 and forming highly reactive CaO. The CaO then combines with silicates and aluminates in the mix to produce the key clinker phases: elite for early strength, belite for long-term strength, and illuminate for setting behavior. This is the most critical stage of the entire process, where even small fluctuations in temperature or retention time can cause underburned or overburned clinker. To keep conditions stable, the control system constantly monitors kiln speed, fuel flow, and gas pressure using heat sensors and infrared cameras. The burners inject fuel in a swirling pattern, creating a long, penetrating flame that transfers heat deep into the material bed. Hot gases from the decomposition reaction are drawn out at the kiln inlet, carrying most of the CO2, while excess heat is recovered and sent back to the preheater. Along the kiln, the material gradually fuses into glowing red clinker nodules, rolling steadily along the kiln axis in the constant roar of fire and steel. The red-hot glow still clings to each clinker as they slide out of the rotary kiln, their constant movement carrying them straight into the cooling system. On the moving grate, powerful blasts of cold air are pushed upward from below, taming the intense heat that's still well over 1,200 degrees. Each clinker slowly changes color as it cools, sending waves of heat rising in steady pulses. The haze of warm air mixes with the fading red light, creating a vivid scene where heat and mechanical motion blend together in the process of stabilizing the clinker's mineral structure. The residual heat from the cooling process still clings to each clinker as they slide into the high-capacity grinding mill, processing several hundred tons per day. Here, the clinker mixes with about 3 or 5% gypsum and mineral additives, such as fly ash or ground granulated blast furnace slag. Under continuous pressure and friction from steel balls or rotating rollers, the mixture gradually breaks down into fine cement powder with a fineness of around 4,500 cm. Fine dust rises into the air, and the reflected light on the machinery creates a scene that feels both mechanical and alive. Automated dosing systems and sensors monitor every batch, ensuring consistent mineral composition, fineness, and strength, transforming the solid clinker into the refined foundation of high-quality cement. The uniform cement powder flows from the silo into the packing area, where the rhythm of the plant is defined by a continuous stream of material. Each empty bag is positioned under the filling nozzle, and precisely 50 kilograms of cement drop in, thanks to a modern dosing and weighing system. The automatic packing line runs smoothly, producing 500-600 bags per hour, creating a scene that feels both mechanical and alive. the sound of falling powder blending with the reflections of light on the metal surfaces. At advanced plants, robots fully replace manual labor, guiding bags into place, filling them, sealing them with heat or tight stitching, and ensuring accuracy in both weight and closure. The filled bags move down the conveyor, where sensors monitor each one, removing any that fall outside the required specifications. Next, robotic arms stack the bags onto pallets with brick-like precision, 40 bags per pallet. As the load is shrink-wrapped, the warehouse lights reflect off the surface of each bag, forming a refined industrial scene where machinery, automation, and precision move in perfect harmony, completing the final step before the product leaves the factory. From factory precision components to carefully controlled on-site assembly, precast concrete construction is reshaping how high-rise buildings are made. Instead of relying on weather and on-site curing, the process emphasizes speed, accuracy, and repeatability at an industrial scale. When construction shifts from pour and wait to assemble and control, the entire industry enters a new chapter, one where buildings are produced much like engineered products. If you want to keep exploring the technologies quietly shaping the modern world, don't forget to like the video and subscribe to the Mandarin Tech channel.